So when it comes to mainstream sewage treatment, we tend to directly connect it to the activated sludge process. It's fair enough, but when it comes to warm climate regions, for instance, Brazil and India, anaerobic reactors have been widely implemented, for instance, as the USB reactor. In this case, in those reactors, organic matter can be efficiently converted into biogas. However, nitrogen leaves the system mainly in the form of ammonia. Therefore, a post-treatment step is required for which trickling filters have been applied in a large extent. These trickling filters, they are typically filled with rock-based support media. And then over the last years, a sponge-based support media has been researched in order to enhance mainly the total nitrogen removal efficiency in the system. Nonetheless, a mechanistic understanding of the nitrogen conversions, in this case, using sponge-based support media in trickling filters, is still lacking. And then that's the core subject of this presentation. So we have the opportunity to assess through a very long monitoring campaign a demonstration scale trickling filter filled with this sponge-based carrier media. And on top of that, we also had the opportunity to gather data on 5 different full-scale UASB-based sewage treatment plants, or STPs, in a broad area in the southeast part of Brazil. These yellow dots, they represent these different full-scale UASB-based sewage treatment plants. And then looking specifically into the data that we got from the experimental demo scale apparatus, we saw that an incomplete ammonia conversion took place. In this graph, we have these black squares, which represent the effluent ammonia concentration, which comes from the USB reactor. And in the red triangles, we have the effluent ammonia concentration from the SBTF, the sponge bed trickling filter. We saw then that we had this 76 on average ammonia removal efficiency. And then we start to question ourselves, why have we observed such an incomplete ammonia conversion? Then this comes to a story with 2 main parts. First, we then start to question if DO, dissolved oxygen, was limiting the ammonia conversion in the system. But then this was just denied because actually DO concentrations in the effluent were reaching the saturation point considering the local conditions. A second hypothesis was raised related to the possibility of nitrite inhibition in the system, but as we can see in this graph, nitrite levels were quite low in the effluent of the trickling filter. Then we came to the second part of this story, and then for this we looked into the data from the full-scale treatment plants that we observed. And in the left-hand side, you have a graph representing the bicarbonate alkalinity in the anaerobic effluent, in the USB reactor effluent, and in the right-hand side, we have, for the same STPs, the same sewage treatment plants, the effluent ammonia concentration. And when we look into those two graphs pair by pair, we can see that the ratio of bicarbonate alkalinity over ammonia was typically around 5:6, which is less than the required ratio for a complete nitrification, which lies around 7.14. Okay, then we kept these experimental indications in mind and then come to model. In order to do this, we developed a modeling structure based on a previous published model structure in our group. And then we adapted, considering the inclusion of a ammonification step, followed by a 2-step nitrification process, and also taking into account the heterotrophic denitrification and also the anamox. Okay, then considering this model structure and looking into the data from the demo scale apparatus that we have assessed, we were not able to see a good match between the simulated and the measured effluent ammonium concentrations. That was because we just used standard parameters in this model setup. Okay, then we adapted some of the model parameters, and we were able to get a good fit between the measured and the simulated ammonium concentrations. In this case, as you can see in this graph, measured concentrations are related to these red diamonds, and the simulated is the black line in the bottom of the graph. Okay, but something was wrong with the AOB in this case. Just to give you an example, in order to get this good fit, we had to adapt, for instance, the Hall saturation coefficient related to ammonium for AOB to a very high value, which is unrealistic considering values published so far in the literature. Good. So then coming back to that indications that derived from the experimental data that we got from the demo scale and also the observations at the full scale, it indicated to us some some problems related to inorganic carbon limitation. Then we included this as a state variable in our model. And then by doing this, second question or another question arose, which is what saturation model should be used? Because if you look into the literature, we could see that there is different possibilities in order to comprise or in order to take into account inorganic carbon limitation in models. They're related to monokinetics, the classical kinetics, the sigmoidal kinetics, and then we dig a bit deep into it. So the first saturation model, or the first model related to inorganic carbon limitation that we have is related to this one that I am showing this slide, using sigmoidal kinetics. The mathematical expression you can see in the left part with the parameters that were published in this study, and then this graphical expression, it's actually the equation, but with different inorganic carbon concentrations. That is just a graphical representation of this sigmoidal kinetics. Okay, but then look, it's the same kinetics for AOB and NOB. And when we apply this to our conditions, we saw a unrealistic nitrite buildup. We didn't have nitrite in our conditions. Further on, we have a different set of parameters, but also using the same sigmoidal kinetics. But in this case, look in this black curve in this graph that is in the central part of the slide right now. If you look into the black square, which we are highlighting this value related to 0.12, this is referring to a relatively high offset and associated positive growth rate of AOB, even when we have a new substrate concentration, even when inorganic carbon is 0. Okay, that's a problem of this approach. Further on, specific to NOB and AN, Anamox bacteria, we have observed very low values related to this Hall saturation concentrations related to inorganic carbon and using different kinetics. We talked so far about sigmoidal, and then for NOB and Anamox, we observed in the literature monokinetics. This is associated to the fact that those organisms are less affected by inorganic carbon. Keeping this into mind, we were able to get very good fits just using the sigmoidal type saturation for AOB and calibrating only 2 parameters related to the sigmoidal type saturation and the oxygen transfer coefficient specific for this system. And for NOB and Anamox, we retained the monotype saturation with that very low Hall saturation coefficients. With this, we were able to finally get a reasonable fit from the measured ammonium and simulated ammonium concentrations. What we need to bear in mind is that when modeling mainstream nitrogen removal from anaerobically treated sewage, inorganic carbon limitation should be considered as a state variable, and a higher inorganic carbon limitation should be taken into account for AOB compared to NOB. I invite you to further check out this story in our recently published paper. And with this, I am willing to answer questions and interact and check interactions with different researchers. Thank you very much for your attention.